Okay, now what is the inverse transformation of x equals u over v and y is equal to u times v with all coordinates positive? So we've seen that we'll, we'd have situations where we have x and y are both written in terms of u and v. We've seen where u and v are written in terms of x and y, and we have to be able to switch back and forth between the two. So let's do that in this slightly more challenging one where it's not just, we're more used to seeing a nice bland situation of like x equals 2u plus 3v, but with u divided by v, the work gets a little more strange. So I'd like to just take the two equations and multiply them together. So x times y, and then u over v times uv. The other thing I'd like to try to do is to take the two equations and divide them. So divide the left sides, x and y, so x over y. Divide the right sides, so u over v, divided by uv, in other words, u over v times 1 over uv. Okay, so then if we clean up this first equation, we'll have the v's cancel there and there, right? So we'll have xy is equal to u squared, and then over here, canceling the u's on top and bottom, we end up with x over y is equal to 1 over v squared. Square root both sides here, and you have u is equal to plus or minus root xy. Reciprocate over here, we'll have v squared. V squared is equal to y over x, and then square rooting both sides, v is equal to plus or minus root y over x. Now we were told all coordinates positive, just sort of the problem itself anticipated that there would be some quadratics going on. So we're just going to say u is equal to root xy with just the plus sign, and v is equal to root with just the plus sign y over x. Okay, cool. We're done with that question. Now, it was just sort of a strangity here going on with the all coordinates positive. Just wanted to practice something that wasn't quite so linear, that's all. Something more quadratic. Now, what about triple integrals? Yeah, so far our work has focused on substitution for double integrals. Now, for triple integrals, the work is essentially the same. It's not very surprising. It's also perhaps not surprising that sometimes the work is just a little more tedious, right? So starting with, let's say, triple integral over the region E of the function f of x comma y comma z, let's say dx dy dz, or whatever order it's in, then you first of all, write a transformation. You'd have to have a certain transformation in mind. So maybe it's like u equals something, and v equals something, and not surprising that there's going to be a third variable which equals something. So these are all three of these are written, u, v, and w are in terms of x, y, and z. But then what you do is you take these equations that are here, and then you'll solve for x, y, and z in terms of u, v, and w. Okay, that's that inverse. So doing that, this inverse transformation business going on again. Then, hopefully not too surprising, that we'll have to write out a Jacobian. It's just going to be a little messier. So the partial derivative of x, y, z with respect to variables u, v, w, it's a 3 by 3 determinant that looks something like this now. So partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of x with respect to w. Now take the next letter here, y, and for the next row, partial derivative of y. First with respect to u, then partial derivative of y again, but with respect to v, and partial derivative of y with respect to w. Last, partial derivative of z with respect to u, partial derivative of z with respect to v, and partial derivative of z with respect to w. Then, maybe once you've computed what that ends up being, depends on the problem, of course, maybe it's not too surprising that you would replace dx, dy, dz with the Jacobian that was just computed. So this notation for Jacobian, right? UVW, then du, dv, dw. Not too surprising. And we will see an example in just a moment.